Problem 55 is quite comprehensive. We've got these tri and tetra and di-substituted cyclohexanes. We're asked to, for each of the following pairs of compounds, determine which compound is more stable. And they say you may find it helpful to draw out the chair conformations. There is no other way to solve this problem. If you can do it in your head, you're probably not watching this video right now. I myself have to draw these chair conformations out, analyze both, and so on. So remember again, the general strategy is you want to draw the chair conformation for this one. You're going to have two possible ones. You're going to draw the two chair conformations for that. You're going to have two possible ones. And you look for the global most stable conformation. Least number of axials, least number of gauche, something like that. And then you decide which one is most stable and then make your call. Okay, we want to identify the most stable one. So let's jump in. For A, we're analyzing this tri-substituted cyclohexane, and we just want to draw both, chair conformations and take a look. So let's draw the template here. Remember how we have the two edge carbons, and we rotate them in such a way to flip and generate the two different chair conformations. And it's a good idea, especially when you get to the chapter 5, to always number the systematic way. So if we are numbering clockwise, we want to number clockwise as well. Okay, and let's go ahead and do that over here too. Now that we have a systematically numbered, cyclohexane ring, we can begin placing the substituents. It may be helpful to you to draw the hydrogens that are missing. And these groups that are just hanging out to outer space as a wedge or a dash are actually your methyl groups, right? So let's go ahead and start positioning things. Now to fill in a template, what I would recommend doing is carbon 1, just draw lines, okay, that go in the correct directions. Carbon 3, just draw lines that go in the correct directions. And carbon 5, draw your lines that go in the correct directions. Okay. So all those series of parallel lines. Now you can begin placing your groups. At carbon 1, we have a methyl group pointing up and a hydrogen group pointing down. In the chair conformation, we don't want to draw wedges and dashes. We want to define up and down based on the relative position of that horizontal dotted line that passes through each carbon. So methyl is up, hydrogen is down. Carbon 3, methyl is up, hydrogen's down. Carbon 5, hydrogen is up, methyl is down. Let's go ahead and draw the other groups. So carbon 1, methyl group is still up, hydrogen is still down. And again, the general trend is that axial groups change to equatorial, equatorial groups change to axial. Okay. So here on carbon 5, be careful. Things really twist around a bit from our vantage point. This methyl group is down in the equatorial position. On carbon 5, this methyl group is down in the axial position. Okay? So down means down everywhere, but equatorial and axial switch locations due to this conformation change. We want to identify axial groups and count them up. Okay? So this has two axial methyl groups, and they are on the same side of the ring, so they're totally bumping into each other. This group here has only one axial group, okay? So far this is the winner, but let's see what this other guy over here on the right looks like. So again, you want to draw the two different chair conformations from your generic cyclohexane. So you should be really good, hopefully much better than I am, at drawing these starting points. And just to be ultra consistent, I'm going to keep the same numbering. I'm going to number this from clockwise 1 through 6, and I'm going to make those groups a very clear CH3 group. Okay, and I'm going to draw the missing hydrogens in with, wedges and dashes as needed. Now remember, again, we number these clockwise still. At carbon 1 and 3 and 5, draw lines that bond to groups in the correct kind of angles for your generic cyclohexane template. Okay, hopefully you have this drawn on a piece of paper somewhere and you can just copy that down. It takes a while, it takes practice to draw those kind of like with nice angles and stuff. Now what we want to do, as we did in the previous molecule on the left side of this page, we want to look at up and down relationships. At carbon 1, we have this methyl group going down. With respect to this dotted line, that methyl group going down is going to be here. At carbon 3, we have a CH3 on a dash, which means down or away. And so carbon 3, down is going to be here with respect to this hydrogen, which is definitely up. Carbon 5, we have a methyl group on a dash or down. So that methyl group is going to be here, which is down with respect to this axial hydrogen. And now we flip the chair. What I noticed right away is that this molecule is awesome. This is going to be our lowest energy because look at it. It has 0 axial groups. So this is automatically the winner. It's going to be the lowest energy of anything I could possibly draw on this page. Look what happens when this does a chair conformation flip. The carbon 1 is going to have an axial methyl group. Carbon 3 is going to have an axial methyl group. Carbon 5 is going to have an axial methyl group. And wow, look, those 3 methyl groups are all on the same side of the ring, so they're just totally crashing into each other. Okay, so we have a winner. Part B, we also have a tri-substituted cyclohexane, and I'm going to number once again clockwise. Okay, and I'm going to go ahead and set up my templates for my cyclohexanes. And so remember to do the chair flip. You take those oppositely marked carbons and you flip around and you form that other chair form. Okay, so those are your 2 chair forms. I'll do that over here too. I would just grab a blank sheet of paper and just copy the 2 forms of chair conformations like hundreds of times on a piece of paper until you get pretty good at just drawing them in there. Okay, so there we go. We got the 2 chair conformations, and we want to number now. Well, hold on. What I did in the other problems was I wrote these as CH3 groups, didn't I? So let's be extra clear what's attached to these carbons. So there's a hydrogen on a wedge, there's a hydrogen on a dash, and so remember that you never have 2 wedges or 2 dashes on the same carbon. So we'll clean this up over here as well. Okay, now let's number our carbons. So I'm just going to make this be carbon 1. There's no right or wrong answer. We could draw many different, depictions of this. But I tend to do things clockwise, and I always pick carbon 1 in the upper right. Okay, so carbons 1 through 6 clockwise. Now, what we want to do is identify where those groups are. Carbons 1, 2, and 3 have methyl groups. So on carbon 1, draw in your lines at the correct angles of where things are usually positioned and bonded. Okay. So a lot of this problem is just getting things set up. Now here's where the thinking begins. We want to analyze each of these things and see, okay, there's a methyl group on carbon 1 going back behind the board, and on the carbon 1 we have a methyl group going down relative to that dotted line. Okay. On carbon 2 we have a methyl group coming up. At carbon 2, up would be above that dotted line. At carbon 3, we have a methyl group pointing down. Down would be down with respect to that dotted line. Okay? When I look at this structure, I see all equatorial substituents. So I'm guessing that's going to be the winner. That's going to be the lowest energy conformation. I mean, I don't see how you could get better than that. When you flip, what happens to the equatorial groups is they all end up axial. And so let's identify sources of strain. We've got 3 axial methyl groups. These 2 are on the same side of the ring. So there's a lot of strain in this molecule. Let's continue this problem, even though I think that's the answer. Carbons 1 has a methyl group pointing down. That's what the dash means. In our chair, we don't draw wedges and dashes, we draw lines. This is the down position with respect to the hydrogen. Carbon 2, we have a methyl group down with respect to the hydrogen. Carbon 3, we have a hydrogen down with respect to a methyl group. So this molecule here has strain associated with it. This one, by the way, has no strain. Well, it has gauche interactions, but it has no axial strain. All right, so this has strain associated with it. Now, when we do the chair flip, remember equatorial changes to axial for each of those hydrogens, each of those carbons. So here's an equatorial, it changes to an axial. Carbon 2, the axial methyl group changes to equatorial. Carbon 3, the axial methyl group changes to an equatorial methyl group. And so let's remove that there. So let's look at sources of strain. Axial groups have strain, right? So here's an axial group. Okay, so this has strain. So, yep, that's the answer. Sometimes it's the first molecule you look at. Sometimes you got to look at all 4 to be able to identify it, okay? So these strained ones are higher in energy. This one has no strain. It's definitely the lowest in energy, so great. Problem 455C is just like my other video, problem 49C. Check out the video link below. Problem D, I've never worked this one, I don't think. Let's go ahead and just number things clockwise, as I usually like to do. If you number clockwise, always be consistent to number clockwise, especially in your chair cyclohexane template. So let's draw the template here. And remember to draw the other chair conformation. You take the two opposite carbons and you twist them around each other and you get to this form. Okay. Same thing here. So practice drawing those. Hopefully you get better and better and better as time goes on. So again, what I want to make sure I do is number clockwise. So I don't randomly put substituents every which way. Okay. Most of the problem is just kind of setting up the template and getting things squared away. If you switch one of these and you do it counterclockwise, you'll accidentally draw the enantiomer or something else. For this problem, it doesn't matter, but for some it really does. So let's see. Now what we want to do, as I like to do, is make sure that we know that these are methyl groups, and I like to draw the hydrogens that are on each of the carbon atoms. Remember that you'll never have two wedges or two dashes. You'll have one wedge and one dash on each carbon atom in the wedge dash drawing. So I'll clean up these structures and make them even more clear to my liking. And this is only for clarity. You don't need to do this step as you get more and more advanced, but I like to be super clear for myself. So here's carbon 1. We'll switch over to a yellow color for our substituents. Carbon 1 has a methyl group up. So there's two bonds right to this carbon in yellow. The up one is definitely here. Carbon 2. We have a methyl group down. Draw your two lines. Okay. This dotted line tells me which way is up and which way is down from the side view. The methyl group is here, which is pointing down. Carbon 4. Draw your two lines that we know are orientated in that angle. The methyl group is down. That's here. Carbon 5, draw your lines. The methyl group is up, which is here. Okay, so let's count the axials. 1, 2, 3, 4. This has a lot of strain. Let's do the flip. So when you do the flip, first thing you might want to do is just sketch in the bonds that are to each of these carbon atoms that we have substituents on. Carbons 1, 2, 4, and 5. Now, it's easy now that we see the first conformation. All the axial changed to the equatorial, and all the equatorial, which we don't have, changed to an axial. So all of these methyl groups are going to be equatorial. And when you look at this one, no strain. So I'm going to guess that that's the lowest energy conformation. To continue the problem of analysis, let's look at this isomer. Isomer. It's kind of like a cis-trans isomer. You'll learn more about this in Chapter 5. So this is an isomer. Let's sketch in bonds on carbons 1 and 2 and 4 and 5 in a nice angle according to a template that you might have on a blank sheet of paper or in your textbook. So on this top conformation, let's look. We've got a methyl group pointing up, so that's up in this drawing. We have a methyl group pointing down, that's down in this drawing. We have a methyl group pointing up, that's up on this carbon. And we have a methyl group down, that would be here in this drawing. Let's analyze strain. we've got 2 axial groups, so that has strain. Do the chair flip. Axial and equatorial groups are going to become transposed or appear to switch. So carbon 4, we've got the axial methyl equatorial hydrogen. Carbon 5, we have an axial CH3 and an equatorial hydrogen. Okay? So axial changes to equatorial. Now remember, equatorial methyl groups might experience some strain due to Gaussian reactions, but let's look at the axial strain. There's an axial methyl group, there's an axial methyl group, so this has strain. So my guess in the beginning was correct. This guy here is the lowest energy because there are no axial methyl groups compared to the other conformations which do have axial methyl groups. All right, so thanks for watching. Please subscribe. I hope you like watching some of my videos that show